Our next speaker is Patrick Belmont from Utah State University. He's an associate professor of hydrology and geomorphology in the Department of Watershed Sciences. And he's going to talk about storage and storage related to drainage and the watersheds here in southern Minnesota. He's done a lot of research on that. Let's give a welcome to Patrick.
Thanks very much. I'm excited to be here chatting with you. If you finish your plate and you're still hungry, don't hesitate to go back and get some more. I'd like to talk a bit about targeted water storage. And I live out here in Utah, but I work here. It's kind of a long commute. But it's a lot more interesting in a lot of ways. And that's the reason I keep coming back here. I tend to spend 2 or 3 months out of the year here in Minnesota. Been working here 8 or 9 years now. And there's a lot of good, fun science that's going towards making important decisions. So I've got a lot of people to acknowledge. I'll be presenting work from a large group that I'm collaborating with, faculty members from across the country, a bunch of students, other collaborators and postdocs, and many other researchers whose work I'm interweaving with. We've been funded by a wide variety of federal and state agencies and industry groups. And I have to acknowledge there's a lot of work that goes on here. Your state and local agency staff have done an incredible job collecting data and information. And it's only because of all that great data that we can do what we do. And certainly, last but certainly not least, just the general interest and support of all of you great South Central Minnesotans. I've never been denied land access once in South Central Minnesota. The greatest hazard is I'll go and ask for land access to get a sample or something, and the farmer will want to talk with me all day. And I don't get any work done, but they're great stories, and I really appreciate that there's that kind of ethic here. Rivers are fascinating things. That's what got me into this business. These rivers are dynamic, they're self-formed systems. They form all these amazing patterns and amazing landscapes. And that's what really got me into this business initially, is I was wondering, well, what's all the physics and math that explains how rivers work in all these funny ways and why they leave these patterns? And it's a really exciting time to be in the business of river science right now, because we've got all these new tools, all this high-resolution topography data, the LIDAR data that Minnesota invested in for the entire state. We can see incredible detail in the landscape. We've got all these mathematical models that help us explain how and why rivers meander the way they do, and how sediment and nutrients move through river networks. It's a really fascinating time to be a river scientist. I'm a geomorphologist, which a lot of people don't think is a real word. It's a real word. Part geologist, part hydrologist, part civil engineer. Smash all those things together, and you got a geomorphologist. Water's been in the news a lot in Minnesota. That's another reason I love working here. You really have a strong interest in it. You do a Google News search for Minnesota water quality, you get thousands and thousands of articles out there. And it's articles like this that spur some interest, you know. This is an article from NPR talking about Minnesota attracting more water-intensive companies and industries. There are a lot of places that don't have the water they need to support their industries. Well, Minnesota's got a lot of water. If you want to attract those industries here, you've got to have clean water for them. There are big economic implications of that. I was really relieved to hear all the discussion about the buffer initiative, so I don't have to talk much about this. I share some of the same concerns that came up today. And Pat asked the two speakers this morning to make a prediction about whether or not we're going to see a measurable impact, and I will also not make that prediction. But my prediction will be that we'll never get a chance to measure it, because the rule on the books is not going to be all that happens here. You know, the one saving grace of that bill is that they left this, provision in there that you can provide alternative practices as long as you can demonstrate that they're effective. And so, that really leaves the door open to reasonable and smart people making good decisions, and I believe that's possible in Minnesota. So I think we're going to see a lot of those alternative practices going into place. I think that there are more effective things we can do in places than just putting in buffer strips. So there's my prediction, is that we won't get to test whether or not it's going to make a measurable difference. I think we're all on the same page that we don't want to see muddy rivers or excessively muddy rivers, and that's kind of a squirrely term, but you know it when you see it. Nobody wants to see this. This is a ravine head coming down to the Blue Earth River that was not properly protected, and the tile coming in there just really eroded a lot of the ravine head. The number one person in the world who didn't want to see that happen is the guy who owns this land, of course, and he paid a lot of money to get it fixed. We don't want to see these things happen. Everybody's on that same page. They are preventable, so it's a matter of how. Nobody wants to see this happen. I'm going to show you a bluff, a sequence here of, this is the Blue Earth River coming through a hairpin turn here, and here's about a 75-foot tall bluff, and here's a field. This is back in April of 1991. I just left this line here so you have a frame of reference. It's right along the ridge top there. Here's 2003, and I apologize, the images are a little bit washed out from the lights here, but 2008, you can start to see it back up a bit. 2009, still relatively modest flows in these years. In 2011, remember 2010, 2011 were pretty big flow years. Here's a little bit later in 2011. Here's April of 2015. Nobody wants to see that, especially this person. We're all on the same page there. So let me briefly talk about sediment nutrient issues in Minnesota, and I'm going to focus on the Minnesota River Basin, and particularly the Le Sueur. A lot of what I have to say applies to other places of the Minnesota River Basin, and to some extent beyond that. But we've done a lot of work in the Le Sueur River, so I'll reference that quite a bit. There are 336 impairments for sediment, nutrients, and aquatic life in the Minnesota River Basin, as judged by the MPCA under the Clean Water Act. 336. It's kind of a poster child for, well, potential for improvement, let's say. The Minnesota River Basin is the primary source of sediment and nutrients for Lake Pepin, downstream here on the Mississippi. So people have known that for a long time. And back in 2000, Kelly and Nader published a paper showing sedimentation rates in Lake Pepin have increased a lot. So they've gone up from about 80,000 tons per year up to about 800,000 tons per year. Sedimentation in Lake Pepin. And using trace elements, they showed that most of that sediment's coming from the Minnesota River. And it's not coincidental that it starts to go up right around the time when the initial land clearance started here. It's gone up quite a bit since then. But even if you go back before that, the majority of sediment came from the Minnesota River Basin. Even back 500 years ago, Minnesota River is making up 80% of the sediment, despite the fact that it's only making up about a third of the watershed area. So why? There's some funny things going on. Where's the sediment coming from? How much of it's natural versus human-induced? And how can we clean these rivers up? These are the big questions that we've got to answer. Now, Lake Pepin is perhaps the second most famous lake in Minnesota. I'm sure somebody here can tell me the most famous lake in Minnesota. Mille Lacs is often the first answer I get. It's not right. Lake Wobegon, of course. Everyone knows Lake Wobegon. Well, Peter Wilcock has petitioned to rename Lake Pepin Lake Wilbegon, where all the fields are drained, all the rivers are muddy, and all the rain is above average. We know it's disappearing at an alarming rate. We have put a lot of money into trying to solve this problem. This is a plot from the Minnesota River Basin Trends report in 2009 showing conservation easements. Put a lot of land in conservation. These are sediment nutrient management projects from 1997 and 2008. There's 11,000 blue dots on that map. We've put a lot of money into this problem, trying to solve this problem. And yet, we're not seeing sediment reduction. And so people are asking the question, why? What can we do better? More importantly, we're going to put a lot more money into solving this problem. I was blown away when the amendment passed in 2008. I didn't think it was going to, and I give talks all around the world, and I always point out that the Dow Jones was at 8,000, and somehow more than 50% of Minnesotans that showed up at the polls said, yes, raise my taxes to go to environmental improvement. That's amazing, and it's a great opportunity. The money's going to get spent. We're all united in wanting to make that money work hard and get the most benefit out of it. So the question is how? And I think we're getting to some good answers on that. The river has been degraded, and I don't think that there's many people out there who don't agree with that statement. We see mussel populations have gone down considerably. The number of fish species, that's the green graph there, has not gone down per se, but the fish productivity sure has, and some of the top most desired fish species are less commonly caught. Macroinvertebrate species have gone down considerably. We didn't have data for these surveys in the 2000s, but the river's been degraded. If you're still wondering whether or not it has, we can talk more later. I won't go into more detail about that. What are the economic costs of all these things? You know, what's the economic cost of a declining macroinvertebrate? These are just the bugs that grow in the river. What's the economic cost associated with the declining macroinvertebrate population? And we usually give that value the only number we know it's not, which is 0. We know there's some economic value associated with that in terms of that's the food supply for fish and things like that. We haven't counted all these economic costs, that's my point. And maybe we can, maybe we can't, but we can all agree that there are problems and we can solve them. When we started working on this 8 or 9 years ago, the solution was obvious. It's a big corn and bean field. You know, we've seen this story all over. And I'll tell you, I'll be the first to tell you, I came into this thinking this is not going to be a very interesting project. We're building a sediment budget for an agricultural watershed. Obviously, it's a bunch of sediment coming off the farm fields. We've seen this everywhere. Then, you know, I got here and I said, oh, well, there's some interesting things going on. Other people say this is the obvious problem. And it's completely obvious that that's the cause of all the sediment. Or this, you know, this is a little ravine here. Maybe it's all the ravines. People come into this thinking that there's an obvious answer. And what I want to tell you over the next 15 or 20 minutes is that it's a little bit more complicated than that, but I think we've got it pretty well figured out at this point. So I want to talk about, you know, what we know at this point. And more importantly, to the extent that I can in this kind of abbreviated talk, I want to help you understand how we know what we know. I'm not a scientist who's going to come up here and just throw a bunch of models at you and say, hey, believe the model results. I'm really smart. There's a lot of equations in there. That's not the way that we work. There's a lot of different observations that have gone into putting a coherent story together. So I want to help you understand how we know what we know and what the implications are for management policy and restoration. What I can't tell you is what you should be shooting for. That's for you to decide. I'm here to provide information, help you understand what's going to be effective and what is unlikely to be effective. But you need to decide what's desirable and how we get there. There's multiple pathways. They all have costs. And there are costs with the way things are going right now as well, like I said. So let's get into the information. Geologic history makes this a very sensitive landscape. 15,000 years ago, we would have been sitting under a couple thousand feet of ice here. And that ice sheet retreated. It left behind a huge lake that catastrophically drained through the Minnesota River 13,400 years ago. Catastrophic outwash event that carved the Minnesota River down by about 70 meters. So the Minnesota River's here, say Le Sueur or any other tributaries are here. Minnesota drops down. Now the Le Sueur is left hanging. It's got a lot of potential energy. It's been spending that energy down cutting over the last 13,000 years. This is a big event that still impacts how this landscape works today. Here's a photo I took just as I was taking off from MSP Airport. And you can imagine this huge torrent of water ripping down through the proto-Minnesota River 13,000 years ago. So let's set up a landscape that's got basically three major elements to it. All this brown area here are just these low relief, flat landscapes. Low gradient rivers don't move around a whole lot. They're not terribly dynamic, representative of a lot of the upper Midwest. Then you get into what is a green color here. It doesn't show up real well, but these are these really rapidly incising, rapidly down-cutting stretches of river. They're hypersensitive. These have been some of the fastest down-cutting rivers in the world for the last 13,000 years. So, I thought I was coming here for, a sediment budget for a corn and bean field, and then I see this, and I'm saying, oh, there's some good geology to be done here. That has big implications for how the system works now. You get down in the main stem Minnesota River, and it was scoured out. It's soaking up a lot of that sediment that's coming from these down-cutting portions and other areas contributing sediment. As we move forward, when we start to change the hydrology, when we start to change the sediment loading, these three different regions are going to respond in very different ways. We can talk about the implications of that. One of my favorite things about rivers is that they all tend toward a profile that looks like this. So this is starting up at the very headwaters of the river, and this is the elevation as you go downstream. And of course, the elevation goes down, water goes downhill. But the slope decreases as you go downstream in a very predictable way. It's a remarkable thing. It doesn't matter what geology you're in or climate regime you're in, all rivers tend toward this kind of nice concave up profile. And there's good physics behind why that is the case. But what it means is when I look at the Le Sueur long profile and I see these kind of strange places where the slope increases again, I look at that and I say, that's weird. What's going on there? What does it mean for how the river's acting? And it means a lot. We call that a nick zone. It's a nick in the longitudinal profile of what we would theoretically expect it to be. So I'm going to talk a fair bit about that nick zone. This is how it maps out in plan form on the Le Sueur. This is a 2,800 square kilometer watershed, 1,500 square miles. This is about where the head of that nick is. It's about 40 kilometers or 25 miles upstream. Le Sueur is poorly drained. It's got really fine textured soils. It's been down cutting rapidly for the past 13,000 years, like I said. Agriculture and drainage began in the mid-1800s, and they've continued to evolve in effectiveness, intensity, precision, and productivity ever since then. So it's a great story that all of you know as well or better than me. It's nice that the land use, in some way, is pretty simple. This is, to a large extent, an incredibly productive corn and bean field. Of course, at the field-to-field scale, there's different practices happening everywhere, and we need to be considerate of that. I don't need to go into detail about what these are. This is one of the few crowds where I feel confident you guys know what these drain tiles look like and the density at which they're going in. This is an air photo that was taken right after a rain event. You can see they're going in at pretty high density and continue to. The upsides of drainage is, of course, crop productivity is way up. We're growing a lot more than we ever could here with less tiles. This is an image that was released by NASA of fluorescence in July of 2013. And it's too bad the images are kind of washed out, but we're right up here in south central Minnesota. It's one of the highest productivity places in the world. It's 40% more productive than the Amazon in July. We're growing a lot of stuff here. That couldn't be possible without drainage. The other benefit of drainage is, as you guys well know, more rainfall infiltrates into the soil. And so you have less running off the surface. That's a benefit. There are downsides, and some of you have experienced these firsthand. we are concentrating flow in some sensitive places, and sometimes mistakes happen, and usually those get rectified locally. What's less obvious is that we're increasing the amount and rate of water getting into the river. And that's been exacerbating all of this bluff erosion downstream. And that's been a harder case to make until recently. But we've been doing that. It's also raining more. There's no question we're getting more rain. This is kind of a complicated plot, but basically this is total event precipitation. We took every single precipitation event between 1948 and 77, and we just sorted them from biggest to smallest. And so that's represented on this red line. It's actually a bunch of dots for every single event, showing you what the distribution of rainfall events was in that time period. And then the blue, it's 1977 to 2011. And what you can see is that that entire curve has shifted over. So it's getting wetter, and particularly the bigger events are getting bigger. The big events are getting bigger. Between the drainage changes and the precipitation changes, flows are going up a lot. And they've gone up as much here as anywhere else I've seen in the U.S. Flows have really gone up. These are 7 different stream flow metrics, peak flows, low flows, things like that, from 12 different gauges. Tributaries to the Minnesota River and 4 gauges on the main stem, Minnesota River. And if you started in 1940s through 1980s, there's a lot of variability, as there always is in environment stuff. But it's kind of bouncing around a common average value. Since that time, all of those flow metrics have gone up on average. We're also generating this kind of interesting cyclicity here. It's about a 12-year wavelength. So I'll come back to that, but the main point I want to make is flows have gone up. That goes without question. The fact that part of it is due to precipitation changes is not a reason to delay action, but rather I would say it increases urgency to get something done. We've got a stormwater management issue. Let's deal with it. If you haven't seen these bluffs erode, it's fairly dramatic. This is a video that one of my students shot last year. They happened to be out there working on some of our instruments on the river. And I have an undergraduate who's he's always on his phone. So it happened to be out while this thing started to come down, and he really quickly captured this video. It's impressive. We've got a bunch of cameras out there that are capturing bluff erosion on a daily basis. So we know very closely how these things are behaving. It's pretty impressive. That's about a 40-foot tall bluff there. So the big question is, where's the sediment coming from? And if you're looking at a small space, that's not too difficult a question to answer. But if you're looking at a whole landscape, it's a really hard question to answer. A lot of the sediment gets moved around, gets redeposited within the same field. Now, you might have sediment eroding from a bank, but it gets deposited on the other bank. So understanding where sediment's coming from and how much of it's moving through the system is tricky. But we've made a lot of progress there. One of the ways you can answer that question for a watershed is to build a sediment budget. So how much is coming in, how much is going out, how much gets stored in the floodplains. We had a lot of tools to throw at this problem. We had a lot of gauging data. We had all this high-resolution LiDAR data. It's been great to work with. You can identify all the really sensitive zones in the landscape. We were going out with basically a 3D camera, terrestrial LiDAR system, where you can scan bluffs year in and year out and measure with centimeter or quarter to eighth inch precision how much is eroded from one year to the next. It's a tremendous technology. Done a bunch of field surveys, and lots of folks before have done other field surveys you're able to take advantage of. Air photos, where you can measure how bluffs have eroded over time. And you can also measure how the rivers moved around, meandered over time, or widened over time. As the flows have gone up in these rivers respond by getting wider. They're self-formed systems. They decide how wide they need to be. So we've measured that over time. As the Le Sueur has downcut, it left behind 600 little pockets of floodplain, at higher elevation. So we could see how the rivers cut down over time, and we could measure with pretty high precision, how it's eroded over the last 13,000 years. And then we've got some geochemical tracers, just naturally occurring geochemical tracers. Well, cesium is actually mostly derived from bomb fallout, but lead and beryllium are naturally occurring geochemical tracers that we can tell how much of the sediment that we sample in the river is coming from farm fields versus bluffs and banks and ravines. So lots of tools to throw at this to figure out what's going on. This is what's been happening over the last, say, 13,000 years or so. I've got sediment, this is a sediment budget. So I've got all the sediment sources coming in from the top here. This is what's going downstream. This is what's getting deposited in the floodplains. This is what's going out to the Blue Earth and eventually the Minnesota River. 55,000 tons has been going out to the Blue Earth and Minnesota rivers on average over the last 13,000 years. About 50,000 tons of that's coming from bluffs, banks, and the channel downcutting. Another 11,000 from the ravines. We don't know how much is coming off the field or the uplands over that time. They were covered in tall grass prairie and wetland. We don't know what it is, but it's probably a very, very small number. Similarly, when you go above this nick point, this steep increase in slope, we don't know exactly what was coming out of bluffs and banks up there, but we know it was a relatively small number because there aren't big holes in the ground, right? So we closed the budget for 2000 to 2010, and this is what the sediment sources and sinks look like over that time. The whole system has been amplified. Okay? 107,000 coming out of bluffs within the nick zone by itself. Another 24,000 coming out of banks from meander migration on the river and channel widening. Uplands in the nick zone are contributing about 23,000 tons per year on average over this time. And above the nick, that makes up 75% of the watershed area, contributes about another 45,000 tons. So, this is about 70,000 tons per year on average. It's not a negligible number, but it's certainly not dominant. But we've put some good numbers on all these things. And this, I think, changed a lot of people's perspectives. Some people who thought, well, it's almost all corn and bean fields. We know there's a lot of erosion going on. It must be all corn and bean erosion. Well, no, it's not. Other people who said, well, we know it's all bluff erosion. Well, no, it's not. It's a combination. And we've put some good numbers on the distribution between the two. So that's great. We put that together for the Le Sueur watershed. Like I said, 1,500 square miles. It's a pretty big area to be working in. But I wanted to go to a bigger scale and see what Lake Pepin could tell us. So I went back into those sediment cores and used geochemical tracers, beryllium-10 and lead-210, to figure out how much is coming from fields versus near-channel sources over time. And I went back 500 years. And basically, what you need to know is that low concentrations of these two tracers mean it's primarily banks and bluff sources. High concentrations mean that it's sediment coming off farm fields. So you go back 500 years and it's low concentrations. All the uplands were covered. Most of the sediment's coming out of banks and bluffs. Mid-20th century, we see this big spike of sediment coming off farm fields. Got high concentrations of both of these tracers. A lot of farm erosion, a lot of big tractors, less conservation going on. That's pretty easy to explain and obvious. But what was surprising to a lot of folks is that if you look more recently, the geochemical signature has shifted back. And it is largely dominated by near-channel sources. Like I said, it's not all near-channel sources, but it's dominated by near-channel sources. So here, this corroborates the same story we put together in the Le Sueur at a much smaller scale. And puts a little time element into it to show that, 50 years ago there was a lot more field erosion. Now, we've actually done a good job of reducing field erosion. It's not perfect, but we've done a good job reducing it. And unfortunately, we've just shifted the source, though. The amount of sediment has not gone down because all the gains we've made in reducing field erosion have been offset by channel erosion because we're putting more water into the river more rapidly. So it's a shift. That changes the mindset of, well, we got to do more conservation tillage, things like that, to, some of those things might help, but we have to be thinking more about water runoff. And that's the key point that I want to make here. So quickly, 5 summary points, and then I'm going to go into just a couple of more slides to think about where we go from here. This is some of the most productive ag land in the world, and local economies and communities depend on it staying that way, and I don't see that changing in any way. This landscape's geologically primed to generate lots of sediment. It's generating more sediment than it has in the past, but it's a little bit of a complicated story as to why. Agricultural drainage has significantly increased flows in the river, and it's also raining more and more intensely. We've got some real water management issues to deal with. Ag erosion dominated 50 years ago. Today, most sediment comes from near channel sources, amplified by all these increased flows. So the upshot is we need to manage water runoff better. Okay? Last point, these rivers really are special, and that's why I keep coming back here to work. They're amazing rivers. I just canoed the Le Sueur and part of the Watonwan a couple days ago. They're beautiful rivers. They have been pretty severely degraded. And more importantly, maybe they have great potential for improvement. By virtue of the fact that they are hypersensitive systems, when you treat them well, they'll respond, and they'll come back fairly quickly. There are other parts of Minnesota that don't have that going for them. Better water quality benefits biodiversity, human health, recreation, industry, land use values, all kinds of things. We don't always account for all those things well in all the economic calculations we do, but we all know that they all have those values. So a big part of the solution is putting in water detention basins that are going to slow the flow. You can call them ephemeral wetlands or water detention basins. I've learned that there are different people who prefer different terms for them. I'm ambivalent. I want to find places where we can store water in the landscape temporarily. Temporary water storage reduces peak flows. Reducing peak flows reduces erosion of the bluffs and banks downstream. That's the key process. So we've done quite a bit of work, actually, working with a stakeholder group of farmers, local and state agency staff, consultants, to think about how that can be done and what's feasible. So we've identified a lot of different locations throughout the Le Sueur watershed where we could potentially put in water storage. And they're colored by their distance from the outlet because that's how long it takes for water to get there to the outlet. And what we're ultimately trying to do is desynchronize the peak flows. Desynchronize the runoff so the peak flows come down in the Nick zone. It looks like lots of color in here, but that's just kind of the way the map came out. What we're talking about is 0.5% up to 7.5% of the landscape. That's what we've modeled so far, and I want to show you what those results suggest. The big benefit is if you reduce flows upstream, you're going to reduce peak flows downstream, and that reduces the bluff erosion. This is a plot that shows river discharge and sediment supply in that incising zone. That's where a lot of the sediment's being generated. And what it shows is, as river discharge goes up, not much happens. Until you get to some threshold and you start to get a little bit of sediment. Then you get a little bit beyond that, and you start generating a lot of sediment. So if you start storing some water in the uplands, in a small fraction of the landscape, how much water you have to store to pull yourself back down that end of the graph and spend more time in here rather than up here? That's the question we're asking. It turns out it depends on how many of these detention basins you put in, but also how long they're storing water. If you're just storing water for 12 or 24 hours, you're not going to reduce peak flows that much. If you're storing water for 100 days, well, the next time a precipitation event comes through, most of your storage is already full, so you can't really use it. So there's this Goldilocks zone, somewhere around 5 to 10 days of residence time, where you start to get some really big benefits. If you just put 0.5% of the landscape back in, that's 35,000 acres. These are the benefits you get in terms of sediment reduction down in this incised zone. If you put in 7.5%, we're talking about this orange line. You're talking about a 70% reduction in sediment in the incised zone. It's a big, big number coming from a relatively small part of the landscape. And the thing is, we only were using the natural depressions in the landscape right now. I have no doubt that when people start looking at this, they're going to identify places where they can just slightly engineer the storage to store twice, maybe 3 times the amount of water. You might be able to cut that number in half and still get the same amount of water storage. For those of you who think in these terms, for the 4% scenario, we're talking about storing 1.5 inches of water. It's not a big number, 1.5 inches. For the 7.5%, we're talking about storing about 3 inches of water. It's not a big number. It can make a big, big difference in terms of the sediment loading. But wait, there's more. And this is my second to last slide. But there are other benefits to putting in water storage. This is a data set compiled by Jacques Finley and Amy Hansen. They went and monitored 10 ditches in the Le Sueur watershed over the last year. And they're monitoring nitrogen export. The blue dots are ditches that had less than 3% wetlands or detention basins in their watershed. Less than 3%. The green dots are ones that had just more than 3%. And what you see is a huge reduction in nitrogen export just for that small amount of acreage going into to wetland storage. They did another study where basically they went out and just sampled 94 different locations and looked at how much nitrogen is being exported as a function of wetland and lake. And you see the same thing. You get really big declines with just a little bit of storage. And the declines kind of tail off once you're above 5 or 10%. So you get big reductions in sediment erosion downstream. You get big reductions in nitrogen locally as well as downstream. Two substantial benefits coming from one practice. There are a lot of great examples out there to follow. This is a set of detention basins that was put in by the University of Minnesota Southwest Research and Outreach Center. They've been monitoring this very carefully to understand the effectiveness and some of the issues with these things. Chris Leonard led a group on an Elm Creek restoration project that was monitored very carefully, got a lot of good data out of that. County Ditch 57, many of you are familiar with it. ISG built within the last year, I believe. This is Swift County Judicial Ditch 8 that Joe Magner and Lori Kreiter worked on, a 2-stage ditch. There are a lot of great examples out there of how we can slow the flow a little bit. So, last slide. What needs to happen, in my opinion? We need to slow the flow. We need to store more water in the landscape. That can happen by making better use of existing water storage sites. There are already a lot of them out there. Some of them could be improved. We will most certainly need to install some new ones. Where can we do that where they're going to be most effective? Other ideas like controlled drainage and increased soil carbon are only going to help. So the extent to which those make sense to implement, it's going to help the effects of slowing the flow. 3 short corollaries to that. You need to detain the water long enough so it reduces the flows downstream. That's the ultimate goal. So, 12 or 24 hours, there may be some places where that helps reduce the peak. But in a lot of places, you're talking about 5 to 10 days of water storage in order to reduce the peak downstream. So as we coordinate efforts, that's the key thing to be keeping in mind. Secondly is we want to make the most of all of that land. Certainly we can build in habitat benefits. Certainly there will be nutrient reduction benefits to slowing down the flow. But we might be able to build these structures in different ways so that you'll get more or less nutrient benefits out of it. Maybe they can be done in ways that you're able to hay these areas in dry years. Probably not every year, but maybe in some years. Thirdly, I recommend that we move forward on a path that's going to put permanent improvements in place. And that's a touchy word because as a geologist, I know nothing's permanent. But let's think long term about this. You're going to spend a lot of money putting a lot of these things in place. A lot of time and energy is going to go into it. Planning, installation, maintenance. A lot of these things can be ripped out in an afternoon. If we're going to make all of these improvements sensitive to the price of corn, what's the point in doing it? Okay? Let's do this in a way that we're going to have permanent improvements down the road. We should continue to maintain and improve field practices. Certainly there are things that we can do to reduce that 70,000 tons per year coming off fields in the Le Sueur. And lastly, this is one that's been talked about a little bit, but certainly this needs to be done by providing incentives to people who are going to be doing the work and incurring a lot of the costs. What are those incentives going to be? That's up to you guys to decide. That's completely above my pay grade. But the other side of that is it needs to be done in a way that's got minimal red tape. We've already heard from a couple of folks that, I'm not going to work with the government because it's such a pain to get anything done. And I hear that time in and time out. That needs to be fixed. And lastly, coordinate efforts. The collective downstream impacts really matter. So, I've talked long enough. I'd love, if we have time, to take some questions and chat some more. How are we doing on time, Chuck? Okay, great. Chuck said I can't eat unless half of you clap at the end. But it can be after questions. Yeah.
In the 1850s and 1860s, paddle boats would go up the Minnesota River way past even Mall. They could almost do it, outside of 30,000 miles. So the Minnesota River was a kind of constant flow because there was apparently, there weren't any major events that would raise the river level because there were so many wetlands in the watershed. And now there's no wetlands anymore because it's all big farm. And now we have the increased flow.
The flows have gone up a lot. And absolutely the drainage has a lot to do with that. And there's a large and very compelling data set that shows that. There were other issues going on in the Minnesota River. There were a bunch of dikes and things like that made the river more navigable farther upstream. But yeah, absolutely. There's no question the flows have changed. And that putting a little bit of storage back in the landscape can make a big difference in bringing us back in the right direction.
If I had a 3,000 acre watershed, there was a county ditch, and I agree with everything you said basically, but if I wanted to know where I get the most bang for my buck for retention, can you tell me, if I gave you a 3,000 acre watershed and said, tell me where, based on your review of where I get the most bang for my buck to retain water, is that something you could provide?
Absolutely. We have the data. Minnesota invested in LIDAR data for the entire state, and it's amazing. I think it costs in the ballpark of $3 million. Les, is that? 12 million, okay. Worth every penny. This is really high resolution maps. Every 3 feet by 3 feet area has an elevation. We can see incredible detail out there. And on a field by field basis, absolutely, we have all the tools we need to make the right decisions about that. You're going to want to treat as much of the land as you can, as the general idea. But how that happens and how it makes sense has to be done on a field by field basis.
To sell it, people in the watershed say, where's the best place to put it? It's always on the neighbor's property, that sort of thing. Yeah. But assuming you took that out of the equation, there's some data that we can provide to say, we'll get the most bang for the buck at this location.
Absolutely. So, it's an important point that right now, it always looks like it's better to put it on the neighbor's field. How does Minnesota turn around the incentives for some more people to stand up and start saying, no, if you're going to pay me that amount, I'm going to put it right here. That's I think, what people need to hear from more of you guys. The incentives have to be there. I think that there's the will, and I am not a politician by any stretch of the imagination, but I think there's the will to make it happen if people start saying, this is the incentive I need, either put up or let's stop talking about it.
Building off of what Kurt said is, right now the way we do wetland restorations, we do a lot of things, particularly in the Minnesota River, is first come, first served. There isn't really a strategic approach that is based on the hydrology of that major watershed. And I'm not sure that we've got the hydrology in all the watersheds to do exactly what you said at this point in time. How detailed of hydrology do you believe you need to be able to implement this?
So that's a great question. We have done a lot of work in the Le Sueur, Blue Earth, and Watonwan. And we've done that to a large extent because that is the bleeding, muddy heart of the Minnesota River Basin. This is where the sediment loads are the worst. This is where, to a large extent, the nitrogen issues are the worst. And it's a place where we know we can make a lot of improvement. We're also working at the scale of the entire Minnesota River Basin. But it's a different beast. You start going upstream on the Minnesota from here, and you run into a very different landscape pretty quickly. And so it needs to be taken into context. I want to focus on this landscape right here because I think it's the priority. It's a place where we can make the most progress and demonstrate to everyone else that it's really going to work. But I don't have any doubt whatsoever that we've got all the flows and sediment loads and nitrogen loads measured well enough that we can go to any other place in the Minnesota River Basin and say, over a matter of 2 to 3 years of study, this is where we're going to prioritize doing stuff. And it's a matter of deciding what that stuff is that's going to be most effective.
Just to follow up to that, I can attest that that makes a big difference. Working with the watersheds in the Red River Valley, we've done exactly that.
Right, absolutely.
And will have a significant impact on inflows on the main stem of the Red River once we implement it.
Yep. Absolutely. Red River is another great case study of people getting together, rational people getting together, looking at all the data and figuring out a coherent plan.
Okay, you people from Toyota, they're talking about reducing flow. Upstream here, about 100 miles from here, up at Granite Falls, is a 14-foot dam with the blessing of the Minnesota DNR, took the dam out. Anything behind that dam was flushed downstream. The banks are eroding on the south side. How can that be explained by the state then? They did not reduce the flow, they increased the flow. The idea was to have it for fishermen to fish upstream. The fishermen now said there's no fish upstream. There was a big natural water pond, about a 10-acre, and that's all gone now.
Yeah, but in the grand scheme of things, that wasn't storing a whole lot of water. It's a small amount of water relative to the entire watershed. So I'm not going to defend the DNR taking that dam out or not. I don't know much about it. We've done a bit of mapping up there for this Asian carp issue that's coming up. But
Water 6 inches in the city of Granite Falls, and they're dropping maybe 6 to 8 feet. Geology is not working there.
I won't defend the DNR because I don't know a whole lot about that specific case. What I can say is generally speaking, putting in more water storage is going to get us head in the right direction.
Water storage, we're putting big efforts and buffers. Are we putting our money in the right place?
Chuck, we still have time for questions. So the question was, we're going to be putting a lot of money, time, and effort into buffers. Are we putting our money in the right place? Like I said at the outset, I'm not going to predict the amount of sediment reduction that we get or water quality improvements if the bill is implemented as it's written exactly. I think the real saving grace of the bill is that they leave the option for alternative practices. And Greg Mickelson brought up, if I have a berm that's going to stop the water from getting in there in the first place, well, maybe a 5-foot berm is going to be more effective than a 16 or 50-foot buffer. And if you can demonstrate that to your SWCD officer, that might be an effective practice.
I'm an engineer. How much proof do I have to get to prove that?
Great question. I'm the wrong person to answer that question. Maybe that goes to Kurt, or maybe it goes to the SWCD folks. But it's an important question to ask. I've been working with a lot of people here. There are a lot of people who really care, who really want to get it right, and who really, more than anything, don't want to waste money. And so I have high confidence. As an outsider, I have high confidence that Minnesota is going to move forward in a smart way on this. We're going to see a lot more of the alternative practices coming in. We're not going to put buffers in places where they don't make sense, or we're not going to extend them 16 or 50 feet. We're going to demonstrate that there are other practices that are going to be equally or more effective. I think we're going to use that option frequently. Okay.
Up in the red, they use very large impoundments to do that water storage. It's a different landscape. Do you think that some would actually work in the Minnesota River Basin or not?
I would far prefer to see it happen in smaller areas for a couple of reasons. One is you're a lot more likely to build in habitat benefits. You're a lot more likely to get nutrient retention benefits. With the big impoundments, you're much more likely to create big problems. It's going to fill in with sediment. There's no question about it. It's going to fill in with sediment, and then what do you do with it? If you're doing it in a much more spatially distributed way, it can be maintained at a more local level, and I think you're not setting yourself up for big problems. The other issue with big impoundments is you end up cutting the channel network up for fish, and that ends up being, for the most part, a bad thing. Now, we've got this Asian carp issue that's coming to the forefront. They're near the mouth of the Minnesota River. Those big impoundments would certainly help invasive carp not get into certain parts of the drainage network. But my guess is if somebody really looked at that question hard, the benefits would not outweigh the costs, all of the costs associated with the big impoundments. I'm talking about this specific basin. Yeah. I didn't say anything about the red. It was not me. Thanks a lot.